Texan Global School. Factoring algebraic expressions. The factoring process involves writing a polynomial as the product of its factors. In this class, we will analyze some cases and processes of factoring algebraic expressions. The first case is called common factor. The common factor to all terms of an algebraic expression is obtained by calculating all the terms' greatest common factor. Recall that the greatest common factor of a group of specific numbers is the greatest value capable of dividing all the numerical coefficients of the expression. Thus, for general numbers or variables, the greatest common factor will be the variable with the least exponent of all the terms of the expression. Once the common factor is obtained, we will use the distributive law, seen in previous classes, to complete the factoring. Let's look at the first example. We will obtain the common factor of the following expression. First, we obtain the greatest common factor of the numerical coefficients and the independent term. As we can see, we obtain the prime factors of each specific number to detect the greatest common factor, which is 7. There is no common factor for any of the variables since not all the terms have the same variable. We divide each term by the common factor to obtain the terms of the second factor. In this way, the factors of the polynomial are 7 times 2x squared minus 3y plus 4x minus 8. If we perform the product between the common factor 7 and the second factor, we can verify that the result is correct, if and only if we obtain the original polynomial. In this other example, we first obtain the greatest common factor of all the numerical coefficients of the expression. In this case, it is 4. Now, the common factor for the variable x will be the one with the least exponent of all the terms. In this case, it is x squared. Therefore, the common factor of this expression is 4x squared, since all the terms are divisible by that greatest factor. Then, we divide each term by the common factor to obtain the terms of the second factor. The factors of the polynomial are expressed as 4x squared times 2x cubed minus x squared plus 4x plus 8. Likewise, if we perform the product, we can verify the result. For the third example, we will obtain the prime factors of each numerical coefficient to find the greatest common factor, which is 3. For general numbers or variables, the greatest common factor for a is a cubed, and for b, it is b squared. Therefore, the common factor is 3a cubed b squared. We divide each term by the common factor to obtain the terms of the second factor. Thus obtaining the factors as 3a cubed b squared by minus 3a fifth b fifth plus 4ab plus 5a squared minus 6b. The second case of factoring is called the difference of two squares. A difference of two squares is factored as conjugate binomials. Let us remember that these formulas had already been analyzed in the class of special products. Now we are doing the reverse process. The process to factor these types of expressions involves calculating the square root of both terms, thus obtaining the value of a and b. Subsequently, these values are substituted in the conjugate binomials, thus obtaining the factors that result in the difference of two squares. Let's look at an example. We will factor the following expression. As we can see, it is a difference of two squares, since the expression contains two terms being subtracted, and both terms are the result of a square. We then calculate the square roots of each term without considering the sign. In this way, we can see that a is equal to 5y, and b is equal to 7. We substitute those values in the conjugate binomial pattern. So, the factors of the expression are 5y plus 7, times 5y minus 7. In this other example, we will now factor 121x squared, minus 81y to the fourth. Next, we calculate the square roots of each term. In this way, we can see that a is equal to 11x, and b is equal to 9y squared. We substitute those values in the conjugate binomials pattern. So, the factors of the expression are 11x plus 9y squared, times 11x minus 9y squared. Likewise, if we perform the product of these conjugate binomials, we can verify that the result is the difference of squares. The third case of factoring is the so-called trinomial of the form x squared plus b, x plus c. The algorithm is described on the board. Since it is a quadratic expression, we will then have two factors. The square root of the quadratic term will be the first term of each factor. Next, we look for two numbers that multiply, give the independent term, and add together the numerical coefficient of the linear term. Let's look at an example. We will factor in the indicated expression. We then see that the first term of each factor is x. We then look for two numbers that multiplied give positive 6 and added negative 5. The combinations of numbers that give us these results are negative 2 and negative 3. We place those values in the factors. In this way, we obtain that the factors are x minus 2 times x minus 3. In the following example, we will factor x squared minus x minus 12. We then see that the first term of each factor is x. We then look for two numbers that multiplied give negative 12 and added negative 1. The combinations of numbers that give us these results are positive 3 and negative 4. We place those values in the factors. In this way, we obtain that the factors are x plus 3 times x minus 4. As we have mentioned before, we can multiply those obtained factors to verify if the result is the original polynomial. The next case of factoring is the so-called trinomial of the form a, x squared plus b, x plus c. The algorithm is described on the board. In general, we will use the scissors method to obtain the factors of the algebraic expressions. Let's see the process with an example. As we can see, it is a trinomial of the form a, x squared plus b, x plus c. Since the numerical coefficient of the quadratic term is different from 1, we then calculate the square root of x squared. The result x is placed in the column of the scissors arrangement as shown. Now, we will look for all the combinations, where when multiplying the column on the left, it gives the quadratic term a x squared. And multiplying the column on the right, returns the independent term c. It should be noted that the signs are disregarded. We can see all the possible arrangements. In all cases, if we multiply the column on the left, it gives us 6x squared. And if we multiply the column on the right, it gives us the value of the independent term of 6. Now, if there is a common factor between the rows of the arrangements, then we remove that arrangement. This step helps a lot to eliminate most of the arrangements. We can see that all the arrangements where we identify a common factor are eliminated. The first arrangement is eliminated because the common factor in the row is 6. The third arrangement is eliminated because the common factor in one of the rows is 3. The fourth arrangement is eliminated because there is a common factor of 2 in one of the lines. And so on. With the remaining arrangements, we will analyze the correct one. The linear term of the trinomial, which is the sum of the products in the direction of the arrows, will indicate the final arrangement. We can see that the second arrangement is the only one that can give us negative 5x. Finally, the terms of each factor are placed according to the arrangement horizontally. The signs are placed in such a way that, multiplying in the direction of the arrows, and adding these terms, results in the linear term, negative 5x. Similarly, if we multiply the factors, we can verify that we obtain the original polynomial. The last case of factoring that we will see is the so-called sum or difference of two cubes. A sum or difference of two cubes is factored as the product of a binomial with a trinomial. Let us remember that these formulas had already been analyzed in the class of special products. Now we are doing the reverse process. The process to factor these types of expressions involves calculating the cube root of both terms, thus obtaining the value of a and b. Subsequently, these values are substituted in the product of a binomial by a trinomial, thus obtaining the factors that result in the sum or difference of cubes. Let's look at an example. We will factor in the following expression. As we can see, it is a sum of two cubes, since the expression contains two terms being added, and both terms are the result of a cube. We then calculate the cube roots of each term without considering the sign. In this way, we can see that a is equal to 3x, and b is equal to 2. We substitute those values in the formula of a binomial by a trinomial. So, the factors of the expression are 3x plus 2 times 9x squared minus 6x plus 4. Texan Global School. Global online learning. Knowledge for the world. www.texanglobalschool.com